So today's presentation is based on student industrial projects, and the title is Selecting Best Leads for Depot Operations, and this is a specific case study for Amalfi. So this is a brief training introduction for some of you who don't know me. My name is Goro Malakayo, South Sudanese, and I'm currently studying at the University of Technology Electronics in Malaysia. And the program is mechanical engineering, and I'm a supervisor for the current training period of some Then just a brief background on my university. It was established in January 10th, 1997. It's one of the top private universities in Malaysia, and predominantly gives engineering courses, mainly engineering courses. And one unique thing about the university is that in the country it gives the longest industrial training, 7 months. And what this basically helps is it gives the trainee significant opportunity to actually interact with the engineers in the workspace and actually get to blend the engineering knowledge that you have, the theoretical knowledge that you have, with the practical work you can get experience. And I think one of we actually have 2 alumni here. Yeah, over there. And so 2 alumni from the university. And so the overview of the presentation is as follows: a brief description of the project, and we go to the objectives. What are the objectives of the project we wanted to achieve? The scope of the study. So this is basically the data that we used during the project. Then the findings. What are the findings? We're going to discuss more about it. The conclusion, and finally the recommendations. So this is a brief description of the project. So, as you see in the title, is choosing the best drill bits for depot operations. And the case study is on Hamal Field. So this was based on the 2014-2015 drilling campaign, whereby in the Hamal Field they drilled Hamal 23, 24, 25, 28, and also 26. But then the data for 26 was incomplete. As you can see here, this is the field, Hamal Field. So we have Hamal 23, Hamal 24, 25, and 28. And the tools, so the offsets, the tool that we used to study the offsets data was basically, this is it's called parameter training. So this is actually being used in Petronas right now. And my supervisor, Hanif, wanted to, is trying to pioneer it to use Epoch 2. So let me give you a brief description of how parameter training is. So basically, you plot the ROP, rate of penetration, the weight on bits, the torque, the flow rate, the RPM. These are the basic parameters of drilling, together with the lithology column from the master log. So this is from the geology section. And normally they usually also the UCS, you can find compressive strength, but then this is data that's not in Depot right now, but then it's one of the things that if it's added to the parameter training might actually help to see the full picture. And what basically happens is you can actually observe the ROP meter by meter, and you actually check, as you can see, these fluctuations. So basically you can actually trace why is the ROP low in this section, and you actually go across the board and you can actually see, was it because of the weight on bit? Was it because of the flow rate? Was it because of the RPM? Was it because of the lithology, the type of lithology that was being experienced in us? Then you also get to see the type of bit that was being used, and the reason why it was pulled. So in this case, it was pulled with the bits after this section. You can see very low ROP in this section. Then the bit was pulled. The bit was pulled, and once the bit was pulled, you can actually go and see that bit grading. You can actually see how the bit performed. Was it really used, or was it the bit pulled and was still green? So the objective of the project was selection of the best performing bits from the offset data, then highlight optimization problems through parameter training, and suggest possible remedy for these optimization problems. So the scope of study is all the data that are being used. As you can see here, this is the data reports you can find in the operation server, and basically this is a summary of the bits, and basically you have the type, the number of bits that were used in that specific field, the meterage drilled, the IDC bit classifications, and the IDC bit drilling, Then this is the drilling data. This is actually from the sensors from the mud logging unit. So you can get this data from the petroleum engineering sector. Then you have the project cost estimate. This actually you can get bid cost and allow the trainee to use to do cost per foot analysis. Then also the daily drilling report, where you can get how much time was spent on drilling, how much time was spent on pulling the bit out of the hole, running the bit into the hole, and actually and how much time was spent on wiper trips. And finally, the formation evaluation log, where you get the lithology column. So this, the findings are found in the project. So first we cover on drill bit selection based on offset data. So before we go into that, we'd like to show you a general well geometry for Hamal field. So you basically have the first drill at 20-inch hole, and then up to 41 meters. Then the set a 16-inch conductor casing. Then the drill 14.75-inch hole at around 452 to around 460 meters. Then they set a 10.75-inch surface casing. Then they drill a 9.78-inch hole at around 470 and 480 total depth. And then they set a 7-inch production casing. So basically, in the drill bit selection, we're going to classify for the 20-inch hole. We're going to check the number of the bits that were used for each hole section in the wells, and compare the ROP, and then choose the best performing bit. Then the same thing with the 14.75, and same thing with the 9.78-inch. So if you do that, so this is our drill bit performance for the 20-inch hole. Let me just go through the graph. So on this side, on the left side, you can see this is the ROP, and this is represented by this, the red column. While on the other side is the meterage, which is represented by the line. So basically, when you're checking and observing the drilling performance, what you want is a bit that gives you the best ROP, but at the same time also high meterage. These are the two things that you check. So in this case, Rolocon 115 was chosen. This was, you can see this is Hamal 23, Hamal 24, Hamal 25, and Hamal 28. So the best bits chosen was Rolocon 115 in this case, whereby we had ROP was 17.31, and the meterage drill was 36.5, which is not that far from the other ones, which is 6.5. So actually the whole well was built, the 20-inch hole, they only used Rolocon 115. So the selection is actually more straightforward. So the Rolocon, the recommended bit for Rolocon 115, the 20-inch hole, Rolocon 115, and this is basically a mill-tooth bit for soft formation with low compressive strength and non-sealed friction bearing. So as you can see, this is the Rolocon 115. Then for the 14.75-inch hole, so again, so in this case, the trainee chose 2 bits. So why you choose your best performing bit, then you choose a backup bit in case if in the next drilling campaign something was to happen in the Rolocon 117 as a chosen bit, what is your contingency? What is your backup? So you choose a backup, which is represented by the white sample, while the chosen one. Then from the onset, just looking at the graph, you can actually tell that Rolocon 127 actually had a better performance, 20.53 compared to 19.1. But the Rolocon 117 was chosen as the preferred or the recommended bit. Why is that? The thing is that Rolocon 117 and 127 are in the same series, whereby Rolocon 117 is for mill-tooth bit for drilling for soft formation with low compressive strength, while 127 is for drilling for soft formation but medium strength. So basically, we find that Rolocon 127 is a bit heavy because it's drilling medium strength, and it will be a bit more expensive compared to the Rolocon 117. So in terms of also checking the cost of the bits, this one is cheaper and actually gives you an ROP of 19.1, which is not that far from the 20.53. So actually in terms of economics, I'd actually prefer taking this bit, cheaper bit, get a really good ROP, a very good meterage around 4.7. Then in case this bit was to fail, my backup would be Rolocon 127. But then also observing this graph, you actually notice one thing. Yes, I've chosen Rolocon 117 from Hamal 24, had a ROP of 19.1. But if you move here, you can see the same bit was used in Hamal 23, but gave me an ROP of 13. So they kind of ask the question, you're using the same bits, or the same drillers, but then why is one bit performing well, while the same bit, another well, is performing badly? So later on, we're going to check on optimization problems. Some of the optimization problems could have led to this. And same thing happened with roll on 127, whereby in HAMR 25, gave a 20.5 ROP, while in HAMR 28, gave a 12.4 ROP. So the roll on 17, as I said, is a milled bit for soft formation with low compressive strength and sealed friction bearing with bridge protection. Bridge protection, while roll on 127 is a milled bit for soft formation with medium compressive strength and a sealed bearing with bridge protection. And finally, the 9.7/8 inch hole, and the chosen bit was roll on 117 again, which gave a performance of 14.65 with a meterage of 521 meters, while the backup bit chosen was PDC. This is BD50XL, the Chinese bit. So the IDC classification is actually PDC and 3D1. It's a matrix body. So it's actually a matrix body PDC bit for soft formation, soft medium formation with a 13mm cutter and short fishtail cutter. But the recommended bit is Rollicon 117. So from this, what you notice is the first thing is the amount of bits that are used. It's something you can notice different from other whole sections. And you can see from HAMR 23, they actually used 5 bits. 1, 2, 3, 4, 5. 5 bits were used. HAMR 28, they used 4 bits. But then if you look at HAMR 24 and HAMR 25, they only use 2 bits to drill for that same whole section. So from observing this, you can tell that why is it that HAMR 23 and HAMR 28 use so many bits, while the same whole section could actually be drilled with 2 bits. So now, the second part is optimization problems from the observer. What are some of the optimization problems that are experienced while the 2014 to 2015 HAMR field? So this is a general ROP of the wells. So you have the depth drill. So the first well to be drilled here in these 4 wells was HAMR 24 between 28th to 17th February 2015. The rig was rig 77 and the ROP was 15.12. Very good. Then after that, they moved to 17th to 12th March. Same rig, they drilled the HAMR 23. They had the ROP 9.95. So it kind of raises the question why, in the beginning you have a very good performance. Then when you move to a different well, you have a very bad performance. While it's the same bit. So you'd actually expect that there would actually be a learning curve where you'd have a good performance, then you build from the good ROP to the next well. And HAMR 28, 4th March to 3rd April, this is a different rig, rig 787, had an average ROP of 10.69. And same rig, 787, from 3rd April to 7th, had a HAMR 25, had a performance of 14.92. So as you can see here, there was actually a learning curve, whereby they performed really badly in HAMR 28, but then when they moved to HAMR 25, I think they actually built in some of the mistakes they made and actually had a good performance. While in HAMR 28 is all the way around. So we'll actually want to check what are some of the optimization problems that could have led to then the performance, especially HAMR 23 and HAMR 28. So one of them was inadequate parameter optimization. So basically the driller was not optimizing these parameters and was actually affecting the ROP. The second part was pulling out green bits. So this is actually a consequence of inadequate parameter optimization, whereby the driller would actually feel that the bit was underperforming and he'd pull it out. But then when you do the downward grading, you actually see that the bit was actually not used to full protection. It was not green. The third part was bit selection and decision making while drilling HAMR 23 and 28. So this was a case study into HAMR 23 and 28 to actually see why the 2 wells underperformed. And finally, lost time spent on y-axis. So basically, as I've shown you from well geometry, the 4 wells are actually vertical wells. So normally, when you have a proper mud program, and you optimize the drill bit hydraulics, then there's actually no need to have a bubble. But then, if you check into offset data, which I'm going to show you later, there is a considerable amount of time that was spent on the oil projects and some of these wells. And finally, cost profit analysis of Hamilton. So this is basically the economical consequences of the inadequate parameter optimization is going to be shown in the cost profit analysis. So at first we start with the inadequate parameter optimization. So we start with the weight on bits influencing ROP. And first we start with the Hamilton 3. This is a roller call bit 137. And as from the onset you can see the weight on bit was put really high to around 10 tons. You can see the ROP was affected, went through. Same thing here. ROP around the regions of 10 tons, very low. So weight on bits around 10 tons, the ROP is affected. And same case here. Weight on bits very high, and the ROP is affected. But then when the drill actually reduce weight on bits, you can actually see the ROP had a surge. And generally, just looking for the weight on bits for this column, you can actually see fluctuating. And the average ROP of the bit was 5.9. So basically, you can actually see that the drilling engineers or drilling supervisors are actually not optimizing the weight on bit. The same thing will happen with the same field, rock on bit 137. This will deep into the well. And again, you can see very high, around the region of 10 tons, the weight on bit is affected. At the moment, it goes back now to around 4 to 5 tons. You can see the surge in ROP. So basically, when you use parameter optimization, you convert those data, the drilling data, and actually make it into graphs where you can actually observe the drilling parameters, and basically you can know, you can judge how drilling went through by how they optimize the drilling parameters. And same thing happened with the Hammer 24. In the beginning, the driller put a very high weight on bit, around 20 tons. You can actually see the weight on bit, the ROP being affected here. But the moment we brought it back to around average around 5 tons, the ROP increased and kept that way. And actually you can see the difference between Hammer 23 and Hammer 24 is that in Hammer 24, the weight on bit was actually kept constant. And you actually see the bit had an average ROP of around 20.6. So this actually shows you that how important parameter optimization is. And same thing here, PDC bit. So as you know that PDC actually drills through shear. So actually it's more dependent on the RPM than the weight on bit. Right? Actually it's not that dependent on the weight on bit. So in the beginning, the driller was actually doing well. The weight on bit, keeping the weight on bit low in this case. And you can actually see a very high ROP in this case. But then, for some reason, the driller just decided to increase the ROP. To increase the weight on bits in this case, and actually you can see the way the ROP is being affected. He kind of went down. He maintained it that way. And eventually, the PDC bit had an average ROP around 11.7. So basically, here you ask yourself why you have a very good showing with this low weight on bits, and you have a very good showing of ROP. Why don't you keep this all through the well and keep this showing? And finally, Hammer 28. This is another instance where the weight on bits is a bit reduced. So you can see there's a surge, but then this will be partly because of the formation that is being experienced in that area. But then again, all through you see in Hammer 23, Hammer 24, Hammer 28, how important parameter optimization is. Then this was a case whereby flow rate was influencing the ROP. So in the beginning, the driller went to a very low flow rate of around 500 gallons per minute. You can see it affected the ROP very low, below 10. But then the moment you moved now to the average flow rate of the whole well, you can actually see there's a surge in ROP, and he kept it constant. And the big performed well. He had an average ROP of 22.7. The same case was here, whereby when the driller started out very high flow rates, this actually affected the weight of the business. But the moment he moved back to the average of the well, you can actually see the ROP now responded with it. And eventually, it was kept constant, relatively constant. And the average ROP had a good showing, 18.8. Then the second problem here was pulling up green beats. So I've already shown you Roller 137, whereby the lack of optimization of the weight on bit affected the ROP. And eventually, the bit was pulled out because the average ROP 5.9, very low. But then when you check the double bit grading down here, you can actually check the bit was green. Basically, there's no loss of cutters, there's no dull characteristics, the bearing was effective, the bit was engaged. Basically, the bit close to new. It was not used to its full potential. And the same thing happened here, 4 to 7. It was drilling, the parameter optimization, you can see the weight of bits fluctuating a lot, and had an average ROP of 9.9. Again, it was pulled, and you can see from the grading, the bit when it's pulled is still green. That means it was not used to its full potential. And this was in HAML 23. And again, HAML 28. So you can actually, from parameter optimization, when observe offset data, you actually start noticing when a well has low performance. You actually look into it using parameter optimization. You actually tell that because of human error, the bits of this well being drilled underperformed. And this same thing was in HAML 28, whereby the flow rate was fluctuating, and when the bit had an average of 8.7, it was pulled out, you can see, no downgrading, so it was effectively green. And the PDC, so PDC was running at a very low ROP of around 3.91, and the driller just decided to pull it out, and again, the bit was also not used to its full potential. So basically, so now we'd like to look into what is some of the bit selection, some of the decisions and bit selection that was taken by the driller while drilling HAML 21. So as you can see in the beginning, so basically this is a bit performance graph. So basically this is the depth, and this is the ROP, and this is formation methodology in the cases. So in the beginning they were drilling the surface of 20-inch hole. The bit had a performance around 7 meters per hour. It wasn't that high. Then, when drilling this is the 14-3/4 hole, also not a very good ROP. You can see around 13. Then, when drilling conductor space, so when drilling the 9/7 or 8-inch hole, in the beginning you can actually see an ROP around 10. This is a roller upon 137. It had a very good showing. Not bad. Then, somewhere here, the driller side, then we pull out the bit. When we pull out the bit, roll up on 127, as you can see from down here, the bit had no downgrade. That means the bit was not used to its full potential. That means the bit could have actually continued drilling at the same, an average of this ROP. So he pulled it out, he ran it for bit, roll up on bit 427. Roll up bit 427 had an average ROP close the previous one. You see? We drilled another meterage of around 281. Again, he pulled it out. And you can see from the downgrading, the bit was also green. And he ran in a PDC which gave a very low ROP, and only drilled 60 meters. Pulled it out, ran in a roll-up on bit 117, drilled. When he pulled it out, as you can see from the downgrading, the bit was actually used 2/8 and 3/8 in and outer cutter. One tooth, the bearing, the bit was 1/8 out of gauge. So basically, you actually see this bit was actually used to its full potential. And the final ran in a roll-up on bit 137. So basically, the problem why HAML 23 underperformed is here, this area here, whereby you had this bit was performing well. Then around this area, the driller said, pull it up. Ran another bit, which performed as well as the previous one, and again, made the decision to pull it up. So actually, if this was avoided, if this bit was actually kept to drill a bit longer for this whole section, then if the driller felt, okay, the ROP is actually dropping, pull it out, and running another bit, then you don't have this problem. You'd actually had HAML 23 having the same performance as HAML 24. Don't forget that HAML 24 was drilled first. It was actually the same drill. So basically, it's the same drillers. They actually know the performance of the previous well. And in this case, they still made this mistake. And same thing happened with HAML 28. Again, as you can see, the first two hole sections were okay. Then the problematic was this 9/7 or 8-inch hole, whereby they were dealing with roll-up on bits 117. Had a good ROP around 11. Then it drilled 335 meters. Then they decided to pull it out. As you can see from the dark green, the bit was still green, wasn't used to its full potential. Then the Renin Rolacon 117, then it had a very low compared to the previous one, had a very low, around 6.5. And you can see from the dark grading, the bit selection was probably not good. It was worn out. Then Renin a PDC, again the Renin a PDC bit, and it gave a very low ROP, around 3.5, around 4, and this only drills 21 meters. So actually, if you're checking drilling economics, when you're running a bit and you only drill 21 meters and you pull it out, actually it's costing you more. Because basically pulling it out and running another bit, in terms of you're paying the rig per hour, so it's a very bad performance. And finally, the Renin Rolacon bit 117, and it had a very good ROP showing and drilled until the end. So basically, this, from observing this, you kind of get a picture why Hammer 23 and Hammer 28 had a very bad performance. And finally, wiper chips. So why I'd say this is lost time spent on wiper chips is because basically, if you have a good mud program and you're optimizing the drill bit hydraulics, then you actually don't need wiper chips in a vertical well. So basically, advantages of doing a wiper chip would be improving the whole cleaning. Why the disadvantages was additional rig time and formation damage. Because basically, when you're doing the wiper chip, basically you keep the drill string rotating, so you're pulling it out of hole. So basically, when it's rotating and pulling out of hole, it basically pulls the cutting with it and it's moving. So it actually assists the whole cleaning. But the danger of this is when it's pulling out of the hole, is the danger of the drill string actually hitting the formation and actually you have the danger of formation damage. So I did a case study on the amount of time they spent on the wiper chips. So you have Hammer 23 here. So this we just run through the table. So basically on this side you have the dates of the wiper chip from the daily drilling report, then the time taken for the wiper chip, and to be run back in the hole, how much time it took to do the wiper chip, then running it back into the hole to resume the drilling, the ROP before the wiper chip, and possible meter ready drilled if the wiper chip was avoided. So basically here you'd have the total time taken for the wiper chips was 21.25 hours. And if this wiper chip was avoided, they could have actually drilled 46.5 meters. This is for Hamad, 3.
Please explain to the gentleman, what is it wiper trip? People might not understand.
How?
What do you mean by wiper trip?
Okay, so basically, when you're doing drilling, you check the trip time. So you check how the cuttings are. So sometimes you might feel down the hole, there might actually not be proper hole cleaning. So what you do is you do wiper trip. So basically you pull the drill string while it's still rotating out of the hole, and while you do that, the cuttings at the base of the bit are going to be pulled together with the drill string. So basically this actually helps, and after that wiper trip is done, the drill string is actually tripped back to the previous article depth. So what this helps in is improves the whole cleaning. But some of the dangers are disadvantages of this is additional rig time, information damage. And
so this one they're supposed to do it every how many meters after the drill? How many meters?
Around 10 meters. Normally it's around 10 meters, but when you feel the what's it called?
I think even based on the drilling program, they're supposed to do it. Maybe this one from the drilling reports, maybe after 150 meters or 200 meters, so we need to do a wiper trip. Unless there is a change on the pits, so maybe we need to pull out of the drill.
So anyone understand wiper trip? Wiper trip is basically when you drill, you create a cutting. So the plan is we want to push the cutting up. But after you drill for certain times, when you cover already certain distance, we need to go back clip. Simple analogy is like this: you are cutting the grass from point A to point B. While you cutting the grass from point A to point B, okay, you start moving, but the grass in point A slowly, to increase. Okay, so you want to make sure. You want to clean it. You want to make sure all the grass in front of you is cut, and the one behind that you left, make sure you want to cut this one. So that's what simple analogy. Okay. Here, basically, what we did 2015, every stand, we drill every stand about 3 joints of pipe.
90 meter.
Yeah, 90 meter. Basically, we do the work with 3. International practice, basically, every 3 stand, then we do the work with 3. The reason being because time. Unless you have a severe hole cleaning issue, then you have to do it more frequently.
So that there is no fixed program to do it every 100 meters or one like that.
Currently, we have developed a guideline. We stated in our guideline that if we want to drill this year, we have to follow the guideline every 3 steps, not every step of 5.
Okay. You say something like that every centimeter.
Every
3 step is about 100.
Yeah, around 300 meter. Because one stand is almost 100 meter.
Yeah, 90.
So 3 stand is 300.
About 300. Yeah.
So as you can see, also Hamilton 2, you can actually see they're spending a lot of time, a lot of wiper chips. In Hamilton 4, we have 55 hours spent on wiper chips, and some of this was avoided. Let's say in the case we were drilling, I think this was around 150 meters, then we did a wiper chip. This was avoided because at least drilled sort of around that 3 meters, which was avoided. Then Hamilton 5. So Hamilton 5, you can actually see that there's a lot of wiper chips during the run of the bit. And if this wiper chips is actually, if there's proper optimization of drill bit hydraulics, then you actually have possible meterage drill around 17 meters. If these wiper chips were reduced or at least optimized. And in Hamilton 8, same thing, spent around 45 hours, 40 minutes. You actually see there's a lot of around 40 to 45 hours being spent on wiper chips. And it was avoided, you actually drill around 106 meters. Then finally, so cost per foot analysis, you see, a drilling engineer, we don't usually focus so much on the cost of the bit. What we're more focused on is the cost per foot. Right? Because cost per foot adds the hidden time. And this is the hidden time. Where you have the drilling time, how much time you're spending on drilling, how much time you're spending on shipping. Also, you compute the rig hourly rate, you see. So actually, when you don't optimize the parameters, you actually spend more time drilling, and it actually costs you in terms of rig hydraulics over the drill depth. So actually, you divide by the drill depth. So this actually comes whereby when you put in a deep drill bit, you actually drill 60 meters when you show the PDC. Only drill 60 meters. So actually, you can tell that the cost per foot is going to be very high. So this is a cost per foot analysis in Hamilton 3. So on the 20-inch hole, they use a roller cord 115, and the bait cost is around $2,440 US. The drill time was 5.25 hours. The trip time was 3 and pull it out. The rig hourly rates is around $950 per hour. Then the depth drilled is around 41 meters. So the cost per foot is 105. Then 14.75-inch hole, roller cord 117. The cost was 4814. Drill time was 9 hours, 5 hours. The trip time was 12.75 hours. Rig hourly rates constant, $50. And depth drill was 411 meters. Very quite a sizable meter drill. As you can see, the cost per foot is not that different. It's not that far away from 41 meters drill roller cord. Then now you come to the roller cord 9.7-inch hole. It's new in Hamilton 3, this is a problematic hole. So whereby roller cord 137, you drilled, the cost was $52,554. You drilled 56 hours, trip time was 4 hours, and rig hourly rate was 150, and the depth drill was 262. So the cost per foot of around 233.79. So now comes to the PDC. So remember I told you the PDC only drills for 60 meters to spool up. But then what raises the question is, why are you drilling 60 meters for 33 hours? You see? From the DDR, I did the compilation, and actually they spent 33 hours just drilling 60 meters. And trip time was 12 and a half hours. And the cost of the bit, you can see, very high, like $6,000. So basically, you find this and the cost per foot was $1,219 per meter. So actually, when a drilling engineer does this type of analysis, you actually see the cost of inadequate parameter optimization. You don't optimize the parameters, you have this type of very expensive, the bits are actually very expensive because of the lack of parameter optimization. The same thing with the Roller 137, it cost around 4,254, and drill time was 21 hours, 3/4 hours, and again, depth drill was 92 meters. 92 meters you spend 21 hours, almost a day to do 92 meters. And the cost per foot is 2.5. So cost per foot, basically, when you do cost per foot analysis, this is basically, so one of the thing is, normally you think, okay, I want to have a cheap bit. I want to get the cheapest bit I can get and drill with it. But then the problem with this is, if the bit underperforms, it actually costs you more. But then, why don't you just go for a more expensive bit but a proven quality, whereby you actually get a very good performance while optimizing the parameter optimization, and eventually, actually, in the end, costs you less when you do a cost per foot analysis. So this is one of the things that the question should be raised. And so, I've shown you some of the problems, some of the optimization problems that we experienced in 2014-2015. And the good thing about parameter optimization is it actually lets you identify the problem, because you don't want to go to the next drilling campaign while not having learned some of the mistakes that you done in the previous campaign. So once you do parameter optimization, you get a list of the problems that led to the very expensive drilling campaign or the lack of performance. And what can you do to improve them? So these are some of the remedies that can be implemented to reduce some of these optimization problems. So one of them is conducting drill-off tests. So this is something that is actually a must. Drilling supervisors should always make sure that they should do a drill-off test before they start drilling. I'm going to depth into it. Second thing was bit hydraulic optimization. I've shown you we spent a lot of time on oil pressure, which is something that can be avoided. How can you avoid it? Optimizing the bit hydraulics. And thirdly is new double bit grading method. So this is something I'm going to go through later on. So first we start with the drill-off test. So basically what happens with drill-off test is, it depends. When a driller has a new bit and wants to start drilling. So normally, convention knows he's supposed to do a drill-off test. So this is the step-by-step how to do a drill-off test. So at first you select the minimum recommended weight on bit and moderate RPM. Then basically you increase the weight on bits with standard increments. So in this case, let's say you spend 2,000 lbs while keeping the RPM constant. And you record the average RP. Then you continue with this, continue until the RP no longer increases with the incremental weight on bit. So this is usually done for roller on bit, because you know roller on bit drills through compression. So it's actually more dependent on weight on bit. But then when you're using a PDC since it drills using shearing, it's actually more sensitive to RPM. So another step is, if you're using a PDC bit, you repeat the same steps 1 to 3, but now using RPM that's going to be increased while keeping an average, while keeping the weight on bit constant. And after you do that, you plot the weight on bit versus ROP, and you select the best weight on bit and RPM combination that basically gives you the highest RPM.
Okay, we need to stop there. You guys okay? Understand?
No, can you just explain what?
Yeah, I'll show you the graph.
Drill-off test is?
Yeah. So basically, the graph that I'll show you. So basically, what the driller does is, you can see the weight on bit and the ROP. What he does is, at first he starts with the weight on bit. He fluctuates, increases by 2,000 lbs, and basically he records the ROP. The ROP with this incremental. Then he reaches a point whereby the weight on bit, the ROP stops responding with the incremental weight on bit. You can see the ROP starts reducing now in this area. He stops. Then this is with a constant 80 RPM. Then he does the same thing again using 70 RPM and again with 60 RPM. So you basically plot this graph. You have this graph. So from this graph you can tell that this is around 47 kilo lbs, and with 80 RPM gives me the best RP. So basically the driller takes these two parameters of the weight on bit and the RPM, keeps them constant, all through the drilling up to the depth. So in the case whereby you're drilling with this parameter, you're getting a very good ROP showing, but then the ROP starts getting affected. The drilling supervisor can actually look at the geologist and ask him, okay, what type of formation am I encountering? Maybe there's actually a column of a very hard formation. So actually, because of the formation that the ROP is being affected, not the drilling parameters. But then in the case whereby the ROP still is being affected, we're recording a very low ROP compared to the previous cases, and the parameters you're keeping them constant, then the drilling engineer can actually, drilling supervisor can actually make decision that the bit is actually worn out, pulls it out. So this actually prevents the cases where, as I showed you before, there are actually a lot of instances where the drill bit is actually being pulled out, but then when you do the drill bit grading, you notice the bit is green. Why is this? Because the parameters are not being constant. The parameters are not being constant. So this is one of the ways, if a drill off test is being done, then you find that the drill bit will have a very high ROP showing all through up to the total depth, and if the ROP drop, then the drilling supervisor will actually make the decision of pulling it out, and the decision will be right. So this is one of the things that should be implemented probably in the next way, doing more drill off tests, so that the driller is no longer just drilling blind. I mean, it's just fluctuating. What is actually following certain fundamentals.
Okay,
And
we'll stop there. Understand? Confused? Okay?
No, I'm just going
Going into that. So the term that Roy is using, WOP and RPM, you guys understand what does it mean?
Yeah.
Okay.
Rate of ventilation.
Bakruddin?
Rate of ventilation, ROB.
Okay, RPM, WOP, do you understand what is it? Understand?
Yeah, rate of beat.
So basically what he said, for us to drill, we're going to resist the strength of the rock. So two mechanisms. Number one is you resist the compressive strength. Okay. If I have the paper, we want to break this. The only way to do it is you compress it, so that it will bend and break. Likewise in our rock, our formations underneath certain things. So how do we get the rock strength? More than that is by putting more weight on our drill string, so that we can break. That's the first mechanism. Second mechanism is through the shearing resistance. That's why he talked about the RPM. For us to resist the shearings, we have to rotate. Rotate like when I rotate, I'm pushing in. So once I can resist the strength of the shearing force, and I can break formations. So what happened in 2015 is we noticed it's a slow ROP because our supervisor at the site never realized that we need to do this. Push. What is the best way of beat in RPM for us to get the fastest ROP? You never do that. But this year, no more.
And how often do you do the drill off test?
Whenever you change to the new beat, you want to test what is the best ROP for the beat according to the recommended weight of beat in RPM. That's number one. Number two, whenever you drill a new hole sections, okay, for example, you complete surface hole and you want to go for 978, you need to do the drill of test. Number three, whenever you encounter a different type of formations, then you have to redo it. Okay.
The second remedy would be bit hydraulic optimization. So basically, before I was showing you the instances where the flow rate was affecting my ROP. So basically, before you start drilling, you're supposed to know what is the flow rate that I need. What is the optimum flow? I mean, what is you need to optimize the bit hydraulics. So this is an example of how bit hydraulics optimization is done. So before drilling, these are some parameters you already know. Where you know the hydraulic horsepower of the pump, you have the maximum permitted surface pressure. This is not the hole size. You know the hole size of the drilling, the drill pipe, the diameter of the drill pipe, the mud density, and this is it's called friction pressure, the drill string and the annulus. So usually this is a constant where K and N are constant and Q is the flow rate. So basically, before you start drilling the whole section, this is the constant you really need. Okay? So now, how do I find the flow rate, the optimum flow rate to get the best hole cleaning. So at first, the thing that is known is that what you want is you want to floor it.
Got it.
Okay, so what you want is you want to know what is my optimum flow rate I'm going to use for this whole session and keep it constant. So basically, they usually start with pressure loss across the bit. So normal convention is you want the pressure loss across the bit to be 65% of the maximum permissible surface pressure. So basically, what I'm saying is at the surface you put in pressure. Okay, but you know, but the fresh the flow, I mean the drilling mud is going to go through the pipe, and there's going to be some friction loss. Friction. So by the time it reaches the bit, now the nozzle of the bit, how much pressure do you want to be there? So normally the convention is there has to be 65% pressure, 65% of the surface pressure being the bit, being lost in the bit. So basically, how much pressure should I put? How much flow rate should I put at the top to make sure that at the bit you have 65%? So actually, what you're doing is you're starting with the bottom. So we know that fundamentally I should have 65% pressure loss at the bit. Okay, so this is represented by P bit. So if you do the calculations, N is a constant, 1.86, and PS is the maximum permissible surface pressure when you know it. And you calculate it, in this formula you get this 2,276 side. And if you divide it by the maximum permissible surface pressure, you know it's actually 65% of why did this bit perform that? Why did this perform that? Then from the mistakes that were made before, we can learn from them, and build on it, and have better drilling campaign in the future. And, finally, also to be able to highlight some of the lost time and hidden cost. So whenever you're doing parameter trending, so basically what happens is you do for a certain whole section until they did a wiper trip. So basically when you're observing it, you can tell, okay, a wiper trip was done here. Okay, so you go check. And when you're doing the whole parameter trend, you can notice, okay, actually there's a lot of wiper trips being done. So actually makes you go to look at DDR and check how much time do you spend on wiper trips, what can be done to avoid it. And basically for the next planning, when you're going for the next campaign, you can actually say, you can actually put regulations in place and say, okay, wiper trips should only be done after 3 strands and not like this. So this is something that we've learned from the previous one, and we're improving on it. And finally, so this is basically a recommendation, general training, SAP training. So one of them is, let's say for the future, if Depot was to take more trainees from the university, one of them was the trainees should be more involved in department operations. So I think this is something that Provider really tried. And whenever there was a presentation by any contractor, Luis Lamberger, Pedro, I made sure that I came. I get to see how it is, because as you know, the country is still new and it's developing. And the engineers that are there, we're trying to make sure that the level, international standard is level. And so this is some of the things that if the trainee comes here for 7 months and actually gets really involved in department operations, it actually really helps in gaining more knowledge. And of course, another thing is more field visit. Of course, for me, I understand because currently the field is not that safe because of the problems that we're facing. But then definitely in the future, this is one of the things that should be added. But if trainee gets to actually go to the field and see the operations, get some practical knowledge.
Yeah, you did go into the field.
I went to the field in the previous SAT.
How many weeks?
1 month.
1 month?
Yeah, 1 month.
Walkover, right?
Walkover. So I got to see walkover. Finally, Q&A session. Anybody got a question?
Yes, thank you for the presentation. It's a very nice presentation. And we, like from what you're saying, I think there's very good involvement with the people you're dealing with at the country. And also spending 1 month, I think it's a very nice story. So maybe for the future, like what was put, that's a very nice thing. I just have a few questions. One would be related to page 32. I think that yes. Where this week was selected. Yeah, and you say it drilled for like 32, drilled about 60 meters.
Yeah.
Would that be is just a decision made by the person, or maybe it was due to the formation being hard, and then maybe they wanted something to actually has no big role in bid selection?
The problem is, as of now, we have been drilling about 683 wells since 2001 during bid of time. But nobody make effort to digest, understand what has been done. Okay, it is massive work like what Mr. Roy is showing you. You have to take one piece of data, combine, digest, and try to understand. PDOC and even DPOC, for this time, we have not done it. So that's why if you look at the numbers of wells, it is very ridiculous how come until now we cannot perform. We are still repeating the same mistake because nobody tried to understand. Okay, until now what we do, basically we need to, as you said, proper selection was not done. That's correct. Okay, that's the reason number two. That's reason number one. Reason number two, sometimes due to the poor planning of logistics, why don't we bring a good bid to the rig site? Because of the time consuming, we just use whatever available. Okay, try and error. Okay. So the key issue is actually go back to the pre-planning. What happened downhole, we don't know. It might be we have done the analysis, but when we drill, still we cannot perform. That's different story. Something new for us. But 683 well. Right.
Okay, you just actually answered the second question I was going to ask. I wanted to know what are the types of different bids we have. And I've heard you mention the PDC and the RC. Yeah, so I was thinking, are those on the types available and you select them here? Or actually you select them or they're just available? And then these are what you can deal with. Like,
professionally supposed to be Juba office will decide based on those analysis.
okay.
Because whatever we decide, it comes to the purchasing. Okay. For this time being, we have a lot of surplus bid. Okay. We don't know whether the selection is right during the beginning when we decide to purchase it. So we just simply redo whatever we have. Second thing, because management see, we want to save the cost. If we can push with what available at field now, compared to whether you need to buy or not. Okay. So it goes back to the cost. That's why he's giving the cost.
Yes.
If you need to buy new bid, okay, but if you run the analysis, the cost of new bid, you put into the formula, is much more expensive. The cost of using a little bit slow ROP bid, but it reduce the cost, then we need to charge on that. So which one do we go? Do we want to drill faster or reduce the cost? Sometimes drill faster, but incur cost, involve safety, and the well is not producing, sometimes it's not good.
Okay. So this one is a good presentation because we do like analysis after we doing some wells, because most of this well is built in 2015 and not as kind of repeat of the six and then like my colleague been asking already to meet this mission. Because already I observed from this one, most of the things we change it is still green pits. It's no effect on the teeth, so the color is not crushed, and even the teeth is still there. So this one is our main problem facing during because the division of the company now will the person who said in the big side to the one is you change the teeth. Still this speed is still is okay, or because maybe sometimes it's not the problem. For example, for the BDC, they can use it for the hard formation. But when you build in the like sandy soil, it's not good. And not good as a common man. of the risk supervisor. He's supposed to be aware about all these parameters. Because even they need to consider even the math properties and even the formation based on the offset weight. So they need to know everything. So they need to know kind of everything, like in the well, hammer 23 and hammer 28. So they change the beat many times. Even I remember last time we supposed to reach the TD only about 20 meters.
Right.
So they changed the beat a bit. Yeah. I don't know why they changed it that time. So there is so that the common model, the supervisors is the one, and the big side is the one to give the decision for that time. So every time if they change any bit, I even ask from the population, they need to send a photo. When this bit is still is okay, or there is a problem with it. When the bit hours is already finished, or is still the phone.
Okay, there are three different way of thought. Some people, they want to drill. When they pull out, they want to make sure the beat is good. Some people, another school of thought, think that I drill, I don't care about my beat condition when I pull out, as long as it reach the TD but fast. When I pull out, when I look at the gradient poor, I don't care. So the ideal case, people basically want to combine these two. I want to drill faster, but when I pull out, I want to see my beat condition is still good, then I can rerun. But most of the cases, we don't get this. So you are left with two options. You want to save your beat for next well campaign, or you want to drill faster and crush the beat. We go for second option. We don't care about the beat we can buy, but the cost of renting the rig, the cost of the well is much more.
So we spend more time on the pull out chain the beat again around, and this one, most of the money is possible.
If you want to have both, you want to have a good beat while you're not compromising the ROP, then you need to go and do the thorough analysis on this in some time. That's what we are thinking. I will push on toward this.
Yeah, this analysis is good.
Okay?
So you drill about 6 wells, you need to do like this analysis so you can know the recipe and figures.
I think what I can add is a good presentation. Area for foundation, I can also involve for the trainee to involve the full departmental. For example, if we talk about the operation department, it shall know engineering, section of construction. This is good. Secondly, any trainee, maybe in all people, any trainee can make a presentation because it's encouraged that how they achieve in that duration of the training. And also other departments, they can share the information. And then when they took that information is fully accurate information. Again, the question is not for the presenter. I want to ask Mr. Anif. Last time,
Then I need to check.
yes, and this is the right place I can add. We have a Mariang 19 in Muleta. Last time we commissioning, and after 2 days, water and walkover is done. Is the problem of mud properties, or what is the problem?
You want to know the whole story?
Yes, yeah.
The whole story is this. When we reach the TD, okay, basically when we finish drilling, basically we're supposed to make sure that we have a good hole cleaning.
Yes.
Good hole cleaning before you run casing, before you do anything. We did analysis. We noticed the hole cleaning is not sufficient. That's the reason number one. Another one you have to understand is when you drill, you're using the mud. Mud and cement, they are not good friends. They cannot be together. If you cannot replace the previous mud you use, then after that you cement, then it will contaminate the quality of the cement. That's number one. Reason number two is we run the caliper.